and welcome back to the second part of Module 4.2. This time we're going to talk about electrolytic cells as well as commercial cells. So we will be able to complete our intended learning outcomes for this module, which is to differentiate voltaic and electrolytic cells as well as apply electrochem in our commercial cells. And if we remember, electrolytic cell would be the exact opposite of what a voltaic cell is. So our diagram before, involving the zinc and copper reaction, would be a little bit varied because now we have zinc as the cathode and copper as the anode, and our electron flow would still be from the anode to cathode. So it's now from right to left as opposed to our previous diagram. So we have to remember also that electrolytic cells involve reactions that are not spontaneous, meaning that as long as we don't have an external energy supplies, this reaction would not proceed. So we're trying to force a chemical reaction. So it would need a source of energy in the form of electricity. So an electrolytic cell, again, is the one that consumes electricity for the reaction to proceed. So since reactions are not spontaneous, electrolytic cells could even occur in a single compartment because, again, they would not proceed with the reaction unless an external energy supply would provide the energy needed. So once the electrons have been supplied to the cathode, it is where the reactions could take place. And since the cathode is the one receiving the electrons, it would be our negative pole, and our anode this time would be our positive pole. So this concept is a little bit different from the voltaic cell simply because it works in the exact opposite manner. So in the cathode half cell, once the electrons have been received from the source, it would be forced to undergo reduction so that the zinc ions would build up as a solid in the electrode. So due to this reduction, there would be a surplus of negative ions in the solution. So a salt bridge would be supplying the positive ions needed to balance the solution charge. So of course, our electrons would not magically appear out of nowhere. It would still be coming from the anode side. So your external circuit or your battery serves like an electron pump, which transfers the electrons from the anode again to the cathode. So your anode, as it sends off electrons to the cathode, it would be forced to undergo oxidation, and there would be a buildup of ions in the solution. So this surplus of positive ions would cause the salt bridge to supply negative ions to balance out the charge. So this is what happens in an electrolytic cell. And in an electrolytic cell, we're more interested about the consumption of electricity or the deposition of metals in an electrode. And for us to be able to be prepared about problems related to electrolytic cells, let's first have a quick review about electrical units. So we have what we call as the charge or the electrical charge, which is a property of matter based on the presence of electrons. We could measure the flow of this charge, and that's what we call as the electrical current. We could also relate the electrical charge to the electrical energy if we incorporate voltage into the equation. And again, this energy could be quantified in terms of rate, and we call that as the power. Electrical charge is measured in what we call as coulombs, and it is directly related to the moles of electrons present using Faraday's constant. So 1 mole of electron is roughly equal to this amount of coulombs. Our current is measured in amperes, and it is simply 1 coulomb per second. Energy could either be expressed in joules, which is the standard unit of energy, or also in kilowatt hour, which is what we see in our electricity bills, for example. 1 joule is equal to 1 volt coulomb, which shows that the energy is purely based on electrical charge and the voltage, and we can simply convert these joules into kilowatt hour using the conversion factor. And finally, we have power, which is measured in watts, which is simply 1 joule per second. So with this review and our knowledge on redox reactions, we would be able to solve any problem related to electrolytic cells. But before we do that, let's talk about the application of electrolytic cells, which involves electrolysis and electroplating. Electrolysis is the process of supplying electrical energy in, to be able to induce or cause chemical reactions to proceed. So it could either be used in separation of elements in a solution, or another application is what we call as electroplating, which is a technique that allows metal ions to deposit at the surface of a solid to form a metal coating using electrolysis. So this reaction would not normally happen under normal conditions. So we need to supply external energy or electrical energy, and that's the process of electrolysis for this to happen. So going back for us to practice a bit about electrolytic cells. For example, we are given a cell with a known amount of electric current supplied to the solution of copper sulfate for a period of time. And we're asked to quantify the mass of copper being deposited on the cathode. Again, the cathode is the one that experiences reduction process, and we are given the half reaction for it, since the given is about gaining of electrons, and gain of electrons is reduction. So what we could do is use the given current, which is 2 amperes. That's simply coulomb per second. So we can use the amount of time given to get the electrical charge. And this electrical charge is directly related to amount of electrons using the Faraday's constant. So once we have the moles of electrons, we can use the half reaction to see that 1 mole of copper is equal to 2 moles of electrons based on the balance half reaction that we have. So your moles of copper could simply be converted to mass using the molecular weight, which is also given to be 63.55 grams per mole, which we would arrive at a mass of copper of around 0.79 grams. So another variation of an electrolytic cell problem would be we are given the electrical current and the mass of nickel that has been deposited on a metal object, and we are asked how long would this process take in terms of minutes. So again, we have the current given in amperes, so that's coulomb per second. But since we do not know the time, we cannot directly compute for the electrical charge. But we are given the mass of nickel, so we can compute for the moles of nickel using the given mass and relate the moles of nickel to the moles of electrons using our half reaction. So 1 mole of nickel is equal to 2 moles of electrons in our given half reaction. And this mole of electrons again is related to the electrical charge based on the Faraday's constant. So once we have the electrical charge and the electrical current, we can compute for the time to be around 9 minutes for us to deposit this amount of nickel into an object. So this is again what we call as electroplating based on the process of electrolysis. So you could take a quick break again, pause this video and resume whenever you're ready. So moving on to our final topic for module 4.2 is the discussion about commercial cells. And we have 3 main types that we're going to discuss. The first one is our primary voltaic cell. And this covers all of our non-rechargeable batteries, meaning they are the batteries that we discard once they're already used up. So going to analyze the anode, the cathode, the electrolyte, and the reactions of these batteries, just to give you an idea on how these work or how they differ from one another. So some examples of a primary voltaic cell would be a Leclanché cell, hard to pronounce, an alkaline battery, and a mercury cell. So a Leclanché cell uses zinc and graphite as its anode and cathode, partnered with partnered with a manganese dioxide electrolyte. So our reactions just show the oxidation process and the reduction process in the half reactions, although we can see that there might be an imbalance of charges or substances because we did not show water or hydroxide ions for simplicity in this presentation. So an alkaline battery is almost similar to a Leclanché cell, which uses zinc and graphite, but this time it uses potassium hydroxide instead of zinc chloride or ammonium chloride as part of its electrolyte. So again, we have the two half reactions shown here. And the last type or example that we have for primary voltaic cell is a mercury cell, which is a mixture of zinc and mercury reacting with mercury 2 oxide as its cathode as well as its electrolyte. So we have a variation in the reaction, but again, the general gist is that we have a redox reaction occurring. So one is oxidation and the other one is reduction. So in a commercial cell, we don't see beakers or salt bridges reacting with one another to form the electrochemical cell. So usually they are in a compact manner, such as a battery storage or a dry cell. For example, this zinc manganese dioxide. But we could see that the parts of an electrochemical cell are there. We have the cathode, we have the anode, and these two half reactions are separated by a film, and we have the electrolytes so that the electrochemical cell would be completed. So once we insert this dry cell into a gadget that uses electricity coming from the battery, generated from the battery through chemical reactions, we are closing the circuit and we are allowing the flow of electrons to be possible. And thus, the chemical reactions could occur, the redox reactions would occur, and thus the transfer of energy from these cells to whatever gadgets that use up those that generated electricity. So another type of commercial cell is what we call as the storage voltaic cells, which covers the rechargeable batteries, meaning that the energy could be replenished as long as we supply energy to it. So again, we're going to analyze the anode, cathode, electrolyte, and this time we're going to be focusing on the uses instead of the reactions. So some examples would be a lead battery, a nickel-based battery, as well as a lithium-ion battery for these rechargeable batteries. So a lead battery uses lead for its anode and its cathode, and it uses aqueous sulfuric acid as its electrolyte. So we know lead batteries to be popular in most of our automobiles and other electric motors, powering up and giving the energy needed for us to use these devices. So a nickel battery uses cadmium as its anode in its earlier days, but since cadmium is not too healthy for our cells and the environment, we are shifted to what we call as metal hydrides. So nickel-based batteries use nickel oxyhydroxide as its cathode and potassium hydroxide as its electrolyte. And nickel metal hydride batteries are the ones powering up our electric vehicles and other small devices such as our cameras. And probably the most The one that we most interact with among these types of batteries is a lithium ion battery. So we have lithium in all sorts of its forms as its anode, cathode, and electrolyte. And a lithium ion battery is the one that we use in our mobile devices, such as our laptops, cell phones, and power banks, that we come into interaction every day. So a lead battery looks a little something like this. So it also has the anode, the cathode, all sorts and all parts of an electrochemical cell. So the only difference is it could be recharged so that it could give off energy once again once the cells have been replenished. So we have another type of storage voltaic cell, which we call as a fuel cell, which takes advantage of the fuel oxidation and oxygen reduction, which could be found in some of the newer models of our automobiles. So while this process produces a clean process, since we have water as its product, the cost would be too high, or the handling of hydrogen would would be difficult compared to our normal sources of energy. But still, it falls under the storage voltaic cells. So our last point of discussion would be about electrolysis in electrolytic cells. And one example would be the electrolysis of aqueous sodium chloride. So if we imagine if we have table salt dissolved in water, in a glass of water, once it has been dissolved, that's it. That's the homogeneous phase already. But once we try to input electrical energy into that solution, we could induce a reaction and thus we could get some products out of it. And the electrolysis of aqueous sodium chloride produces chlorine in its oxidation process. And this chlorine gas could be used in purifying our water or even in manufacturing some of our polymers. And the other half reaction, the reduction of water, could produce hydrogen, which can be used in several industrial processes such as synthesis of ammonia and refining of our petroleum products. We could also have sodium hydroxide from this process, which could be used in paper processing and glass manufacturing, among other processes. So electrolysis is one of the common techniques being used to process our seawater in order for us to separate the salts that are present in the solution. So in our day-to-day lives, we may not be aware of it, but we have electrochemistry all around us. And I think that's it for our discussion about electrolytic cells and commercial cells. Again, to conclude, Module 4.2 is all about electrochemistry, and we discussed the following subtopics. We're still under energy transformations in matter. So now that we have finished Module 4.2, I hope that you're ready for our self-assessment questions in order for you to reinforce the knowledge that we have learned. So these SAQ questions would be composed of 3 conceptual questions and 3 computational ones, focusing on cell notation, standard cell potential, as well as problems related to electrolytic cells. So if you need further reinforcements about the concepts, please visit the following references if you have time. And once again, thank you so much. That would be Module 4.2, all about electrochemistry. So we'll see you in the future lecture videos. Stay safe and God bless.